Next up, we're moving into exponential growth and decay models, but we're going to shift the format of the exponential function itself. So we've already been working with a of t equals a sub 0 times 1 plus or minus r to the t. Then we moved in the previous examples to y equals ab to the x, or f of x equals ab to the x. This model here, a of t equals a sub 0 times b to the t over k, is useful when the question provides the growth rate and the time interval. Whereas the maybe the time is in years, but the time interval provided is not necessarily in years. Okay, so let's look at an example here. So a bank advertises that if you open up a savings account, you can double your money in 12 years. Write the rule for this scenario, right? So the double your money scenario, when it says double your money, it's giving you the growth rate. It's saying it's going to double. So your B value is 2. But the thing here is it's not, you're not doubling it every year, you're doubling it every 12 years right now. So the time interval provided right now is 12 years. So in 12 years, your money doubles. And it's an exponential growth scenario here, right? So how do we deal with it? First, we're going to look at the model we're using from up here, right? So a of t equals a sub 0 times b to the t over k. And t right now is time in years, right? Where the time interval provided is 12 years, okay? And the growth, b value, is going to be 2 because it's doubling every 12 years. So let's fill the values in we have. I don't have an a sub 0 value. All we were really given was a growth rate every 12 years, period. So this would be the rule setup. And what we would need to know to work with this rule is the initial value and maybe how many years we were going to work with, right? Okay, so now what we're going to do is express this in the standard format we worked with previously, right? Now, when we express this, your growth rate here, 1 plus r, it's not going to be 1 plus r. You're going to be dealing with a numerical approximation. But the key part is it's not to the t plus 12, it's just to the t in years, right? So what's going to change is the growth rate here is going to change because this growth rate is every 12 years, whereas this growth rate we're going to modify is going to be every year, okay? And you need to be able to be fluid back and forth from either one of these here, right? So how do we deal with this? It's all exponential properties from this point forward and a lot of decomposition in the beginning. So we're dealing with a of 0 times 2 to the t over 12. And our exponent here is t over 12. So this is where your knowledge of fractions and number sense comes together. Let's decompose t over 12 to 1/12 times t, right? That's the same thing. And then what we're going to use now, so that was just number sense and fractions. Now what we're going to do is we're going to use the properties of exponents to express this equation differently, right? So if t over 12 is really 1/12 times t, or even t times 1/12, then we can rewrite this here as 2 to the 1/12 power to the t power. We could also rewrite it as 2 to the t to the 1/12. We don't need to do that. What we want to do is we want t and time here to be our outer exponent, and we're going to take this 2 to the 1/12 and approximate it now, and that's going to be our growth rate, 1 plus r, but in years, every year, as opposed to every 12 years. So approximate 2 to the 1/12 in your calculator, and you're going to want to go to 5 decimal places at this point. Don't round it to the tenths or the hundredths place right away. So this would be the function we would use where t in years should produce the same amount if you use the previous model up here, t in years, right? This is just your growth rate every year. This is your growth rate every 12 years. So if we want the percent growth in this case, we're going to now set this equal to 1 plus r, subtract our 1, and then multiply by 100 to find our growth rate, which is going to be 5.95% growth. per year.